Hello, hello, hello. Welcome, everyone, to the Juliet Dispatch podcast. I am Chris Rakakis, and
I am Michael Thiemann, and today we have two wonderful guests with us today. So, Jesper, who are you?
Hi, I'm Jesper Öqvist. I studied computer science, compilers, and language design at university and got my PhD there. And now I'm working at Cognibotics here in Sweden. And we work with robots, and we're developing a new robots programming language called Juliet, which is the dialect of Julia.
And our fourth and final guest is Philip. Who are you?
Hi, I'm Philip Olhager. I'm a motion control engineer at the same company as Jesper, Cognibotics. I studied engineering physics and automatic control at university and have been working at Cognibotics ever since graduating.
Right, nice. And technically speaking, right now, if you're watching this on YouTube, you'll notice we'll have a fifth guest in the room. It's the big elephant. So today it's the first time that we have company people on the podcast. Actually, they approached us. They said, we're doing this cool thing. Would you like to do an episode about this? So there was some debate whether how we're going to do this because, commercial interests and stuff. But there's no money exchanging hands. And I think the prospect of making money out of Julia might very well be interesting to many PhD students who are currently working with Julia. And just seeing what else there is in Julia outside of academic world might be super interesting. If this is not your cup of tea, then no worries. Just let us know in the comments below, right? But we still hope you will enjoy this episode that is purely technical discussion
about Julia.
What's happening here. And you know where this elephant is from a big warehousing company, or furniture company in Sweden. And this brings us nicely back to our guests.
I should have brought my octopus. I got an IKEA octopus. Similar size.
No, huge thing. I ate the meatballs. That's about it.
I'm sure I have a dolphin somewhere.
Oh, we got the dolphin also.
Yeah.
My kids love the dolphin.
It's a cool dolphin.
So let's get back to our guests here. We had the one sentence bio, but I want to go a bit deeper into who these wonderful people are. When I started doing the research for this episode, Jesper, your LinkedIn about says, I press button on computers. Usually it has something to do with compilers and Java. So now you're on a Julia podcast. Tell us more about this.
So that's outdated. It shouldn't say usually Java because I'm not using Java anymore, pretty much.
You're currently working at Cognibotics and on this thing called Juliet that we'll talk about in a minute. But how did you end up at this place?
Oh,
what is the connection from the background to your where you're currently at?
Yeah, so I've known the founder of Cognibotics a long time. He was actually working at my computer science department when I studied at university, and he recruited me to Cognibotics because he had this dream of building a new programming language for robots. Claes Nilsson is the founder of Cognibotics, and he's been working both in industry with programming robots, industrial robots, and he's been working with studying robots in academia a long time. And he saw that there was this huge need for modernizing robot programming. So I studied compilers. I was working on compiler construction, programming language design. So he recruited me to work on this new language, and we didn't have any idea what the language would look like. We had ideas about requirements that it would need to fulfill. but it was like a blank slate, completely greenfield thing where we first had to figure out, okay, what should the language look like? And we started looking at different languages. And I think Claes had seen Julia somewhere, so he knew about Julia. And we were looking at different existing languages and taking ideas from them and combining them. And so we looked at modern languages like Go, and I was somewhat inspired by features in Java, and then we looked at Julia and some other languages, and then we liked Julia, and we also brought in one of our early collaborators in the project was Fredrik Bagge Karlsson, who is a large Julia contributor. He is a big Julia enthusiast. Right now, I think he's working at Julia Hub. And so I think he also partly convinced us to use Julia. So we started making this language more and more like Julia. And eventually it became so like Julia that it's, I think of it like a dialect. Because there were several things we were not planning to have in the language from the beginning, like macros and REPL. But eventually we've added these things, and it's very similar to Julia.
Philip, you studied robotics and machine learning before joining Cognibotics. So was Julia already a topic before you joined Cognibotics, or like how did you even end up in robotics and machine learning?
Yeah, so I didn't actually study robotics. I studied automatic control. Robotics is one of the main applications for along with machine learning. And my first contact with Julia was in a course, one of the advanced courses in automatic control, where one of the labs had a sort of an interface to the system we were testing on, which was written in Julia. So the very first line of Julia code I ever wrote was to include some file that someone had wrote. So I didn't actually have to write any code, I just had to run it. And so after that, when I did my master thesis, it ended up being that I would work with the same system, which already had a Julia interface. So it made sense for me to write my entire thesis code in Julia. And so that's when I got my first like real hands-on experience with Julia, which was really cool. I had been, as a student, we learned Java and MATLAB were our primary languages.
That's how I was taught as well. Yeah.
Yeah.
With a little bit of C thrown in there as well. Yeah.
Yeah. For me, with a very minimal amount of C thrown in. So working with Julia was really nice because it had the like good mathematical features of MATLAB, but with a much nicer syntax and a really solid type system and package manager and all that. So it was really nice from the get-go, really. So having done my entire thesis in Julia and being interested in automatic control and not really wanting to stay in academia because I wanted a more hands-on application of what I learned, I reached out to a bunch of different people. And so through my master thesis and some people at the institution, I was put in contact with Claes, the founder of Cognibotics. And we had a chat, and me being control guy with Julia experience was a pretty nice fit for the company. So they brought me on, and that was about 3 years ago. So I haven't been with the company for nearly as long as Jesper, but a fair few years at this point.
So you've been using it probably like Julia for about like 5-6 years now or so?
Yeah, something like that, I would say.
And then Jesper, it seems like he came into contact not as long ago, maybe 3 or so years, or?
I think I started, my first contact with Julia was probably in 2019. And that's when we were designing Juliet initially.
2019 is just a year ago, right?
It feels like that sometimes. So I feel old every time. Like now the company Cognibotics it's I think about 11 years old. And so even though you joined 3 years ago, Philip, it's a third of the company's existence. And I joined. I think the company was about 3 years old when I joined. But yeah, time flies.
Yeah.
Okay, this has been a long time in the making. And so, since you both started to use Julia around 6 years ago, like, what was your experience back then? Like, I'm not as long a Julia user, so I think 1.0 was already out by
Yeah, that was the 2018 summer release. Yep.
But I guess it was before the big time to first X improvements happened and
Yes.
stuff like that.
Yeah, I remember the first time I used Julia, it took a long time to compile. And I don't remember what version it was. 07 maybe, or something like that. And then it got really much faster, much more usable, in my opinion. So that was nice.
Yeah, I think the first version of Julia I used was definitely post 1.0. I think it would have been 1.2 or something.
Yeah, and I assume that when you're talking about first time apply, you probably use a good mixture of like Plus.jl with maybe like Julia control systems libraries or pieces like that. Like a lot of the Frederick verse, if I must say, with the Julia control libraries, or what are kind of the packages that you're using for things like automatic control and robotics?
Initially, I wasn't using it for control because my master thesis was more so focused on machine learning. So I was using things like Flux and things like this. And I was also writing most of my, or like doing most of my actual programming in Jupyter notebooks. So it was actually similar to Python. And so I wasn't really bothered by time to first execution and stuff like this, because it was just doing whatever, really. But lately, after joining Cognibotics and like using Julia in my actual day-to-day in software development, yeah, the Pygeverse packages is useful. And I also use a lot of optimization in my work. So things like black box optim and the whole differential equations of JS ecosystem, things like this.
Yeah, that's a recurring theme that apparently Julia has some okay-ish differential equation solvers. I've heard. I have yet to give them a real go.
Actually, the reason, so I'm sort of tangentially involved with the development of Juliet. I mainly work on a different project in quite a small team. And we've written most of our code base in Julia. And the reason we started doing that was because when we tried to do our first like giant optimization problem in Python, it was super slow. And so we tried doing it in Julia with black box optim instead, and it was way faster. So we kind of needed to have that specific functionality in Julia from the start. And since then, we've just been building everything in Julia.
So, but are you still using Julia at Cognibotics for your or for some of your day-to-day work?
For me, I'm using Julia for all my day-to-day work.
Okay.
It's by far my language of choice.
Yeah, I've heard from Frederick that a lot of the analyses and everything goes on in Julia. But I'm curious to dive into this a little bit more because I mean, Black Box Optim is a really interesting package, and it does a lot of good things. Maybe I'll throw up a benchmark up on here. We recently did a lot of benchmarks that of global optimizers. It's like definitely one of the best ones out there. I'm curious what's brought you down that path of black box global optimization rather than gradient based approaches, right? Do you have this like weird lost landscapes, like what and like can you describe a little bit more about what brings you here? Because I mean that is definitely a space for Julia, right? If you have a really big optimization, but why does this show up in particular in robotics?
Yeah, so this is model identification. Basically, what we've done is we've done a bunch of experiments on a robot where we put it in different configurations and we're shaking it with very specific sine waves and stuff, collecting a lot of data, doing frequency analysis of that and getting a bunch of spectrums. And then we are creating a model, setting up the same spectrums and adjusting model parameters to make it match the spectrum. And so the loss landscape is very weird, and gradient-based approaches don't really work, and we don't really know how to make a Jacobian for this type of thing anyway. So it's not quite black box, but it's closer to gray box than an actual clear optimization.
And the global optimization aspect, I assume, is a big aspect of this, like any local optimizers. Yeah.
Absolutely. we did some initial tests with local optimizations, but they would converge very quickly and not at all be very good.
Mhm. Yeah, actually, my first project in Julia as well was actually something with really big global optimizations. It was in for something completely different. It's for development of new stochastic differential equation solvers. But yeah, I actually built a old AMD FX computer to and let it run for an entire year to do this black box optimization. But the MATLAB one would have taken a few actual like decades or so. So the Julia version of that was pretty good. But yeah, running really big global optimizations, I think, is an underappreciated feature of Julia, with a lot of a lot of really good libraries with like
Yeah.
NLOP bindings and Nomad.jl and evolutionary.jl and blackboxoptim.jl, all actually being really good and scoring extremely well on black box global optimization benchmarks. So yeah, it's interesting that you also came to it for using it in a very similar space, because yeah, that was actually the first one that I used as a gigantic Julia project. So
Identified another topic that we'll have to cover in the podcast eventually. But not today. Today we will talk about Juliet and Romeo. So what is Juliet?
It's a language for built for programming robots, and there are specific requirements that you need. So one very important one is real-time execution, hard real-time execution, where we don't really care about performance, the throughput. That's not so important. What is important is response time. So you need to have quick response, need to meet a specific timing so that you can control the robot smoothly. If you imagine that it's moving quickly, and you need to send information to the motor controllers very very quickly, and so timing is very important. And one of the first requirements we had for the language was static typing. And static typing is important because we want to avoid runtime errors, where something has the wrong type at runtime in a dynamic language, then that causes a problem that crashes the program. That's not acceptable for a robot. We need to catch as many type errors as possible before we run the program, when we compile it. So we wanted a statically compiled and real-time language. And we also wanted managed memory. We wanted garbage collection. So if you look at many of the old legacy programming languages for robots, like Rapid, it was developed early 90s by ABB. And in Rapid, I haven't used it extensively, but as far as I know, you have to pre-allocate everything. So you have fixed size buffers for everything you're doing. And if you have some kind of dynamic data that you need to read in from a network socket, for example, then you have to have a big buffer that you can store that in, and then you flush it to disk. And when it overflows the buffer. And so this is very clunky to program with. We wanted dynamic memory allocation, but it needs to be quick and real time. So we wrote our own. We have our in-house garbage collector, which is a real-time garbage collector. So the static typing was actually fits kind of well with Julia, because Julia has the option to declare types everywhere. You can declare parameter types. You can even write local and then declare a type. Sort of. You can write the type local and then a type assertion. And we took that syntax and we modified it a little bit. We have a new variable declaration syntax. You can write local or you can write var. We want to declare all the variables before you use them, so that we can make sure that you're not trying to read a variable that doesn't exist yet. And that's another thing you can do in Julia. You can try to read. You can use a name in a function that isn't assigned anywhere, and then you get a runtime error. So that's another kind of static compilation thing we want to prevent.
So it sounds like this isn't heavily based off of Julia, but adds a few things so that way you can have a stricter static typing and real guarantees for real time when built to embedded devices.
Yeah, and there's lots of other things that are important for robots. Like when you're programming the robots, you want to have a way of pausing the robot while it's running, editing the program at runtime, and then incrementally continuing. So you could add, for example, you pause the robot, it's moved to some position A, then you pause the robot, you insert a command to move to position B, and then you continue the program. Then it will actually move to that position without having to restart the whole program. And you want to be able to pause the program and then move the robot backwards. So you're stepping backwards in the program. And this can be important when you are programming a robot in an industrial setting where you want the robot arm needs to move into a tricky position, and then you identify something you want to change in the program, you pause it, or maybe there's the program aborts because some kind of safety thing was tripped. Then you need to move the robot out of that tricky position. And the easiest way to do that is to step backwards in the robot program. So you tell it to move to the previous point and then move to the previous point and then out. So we built an editor integration with VS Code where you can step forwards and backwards. And we are working with a Chinese robot manufacturer called Estun. They are a collaborator in this language project, and they've funded the development of the language. And they are using this program. They're using the language, integrating it into their teach pendants for their robots. So you can write Juliet code, and you can step forwards and backwards in real time.
Yeah. How well does how well does I mean, I assume that this is based off of something like the reversible computing. I've seen like some of these reversible compilers stuff before, but how well does that work in the real world of robotics though, right? Because do you end up with this something where you say, okay, go 1 foot, or I guess 1 meter to the right, and then you say, okay, well now I'm going to reverse that, go 1 meter to the left, but there's always like errors and things, right? So how well does it actually reverse, right? Do things like floating point errors or measurement errors and all this that somewhat get in the way, or how does this kind of interact with the real world?
Well, there are different modes of running backwards. So one mode is when you are in so-called stepping execution, where you stepwise tell the robot to, okay, run the next statement. It's like in a debugger where you say go to next line. You can do that on a robot also. And when you do that, it keeps a log of all the positions where the robot has moved. And then when you step backwards, it can use this backwards execution log. And then there's another mode when the robot is running in full automation without this single stepping. You're just telling it to run like a normal program. Then it's moving to these different points by calling functions that are called move J or move C. There are different move commands depending how you want to specify the coordinates and how you want the robot to move. If you want it to move in a circular path, if you want it to move in a linear path, Cartesian linear path, or if you want it to move linearly in joint space. These are different functions, essentially. So you have, in your robot program, you will have function calls, for example, move C, and then a point. And then you have another move C and another point. When you pause the program in batch execution or automatic execution, you are stopped at some line in your program. And then when you step backwards, the execution it doesn't have a history in that case. And it will instead just step upwards in the lines of your program and see, okay, we came from this point, so let's move backwards then.
Yeah, so it might not use exactly the same program steps to get there, but the high level functions will be the same. That okay, you move here, then you move here, then you move here, and so it's going to give a move command, and maybe like little controller details and everything are not exactly the same, but it will call the control command to move to here, and then call the control command to move to there, and then figure out how exactly it needs to change its movements and stuff to adjust for inaccuracies that it finds in the measurements and such. It just says, okay, I'm gonna. So you reverse at a high level, not necessarily at a low level. If I
Exactly.
understand.
The kind of point with the robot programming language is to abstract away all the lower level details that the user doesn't need to care about. Like the user doesn't need to care about exactly which signals are sent to the robot and exactly where the robot is to a very fine detail and stuff like this. The user just needs to care about, I want to go here. Let's go here. So the robot programming language is really interacting with something we call a trajectory planner, which, given a certain move command, plans the movement from wherever it is currently to where it's supposed to go in the way that you've specified. So Juliet really just calls these move commands and sends them the way it would usually be sent to a trajectory planner.
Yeah. So I get the trajectory planning aspect in all this. What kind of detailed primitives do you have for things that are complex behaviors? So more than just moving, but also something like grasping and things like that. I assume that grasping probably comes up a lot in kinds of industrial use cases, right? And that might be more difficult to kind of say, how would the user interact with this? Did they say like, move top part down, move bottom part up? Or is there more of like learn how to grasp kind of things? I know that from human robotics companies that using Julia, like I know that some folks in some like the Boston Dynamics Research Institute, whatever the new name of it is, they mentioned all the time like, oh, they need to they need to learn a lot of behaviors with reinforcement learning and all these things, right? How are those kinds of behaviors built into such a system?
Well, there are different complex. There are very many different types of grippers. So you can have a gripper that's just open close, and that's the only kind I've used, and the most common kind where you just say gripper open or gripper close, and then it has some force that it pushes with. So that's
So
very
it
simple.
goes until you give it a measurement force where you say, okay, when you're gripping it with this amount of force, it should stop. Like it has to figure out how much force to apply before it ends. Because I guess if you just tell it to close, right, it would just kind of snap right through whatever material. So you need something in there to kind of describe it or so.
It depends on the application. The gripper I used, it just had a constant force it would push with, and it's not very strong. But that was a cobot, so it's kind of meant for you to. It's meant to be safe for humans to be close, so it won't crush your finger if you get your finger stuck in it.
How much control can I have in Juliet to just directly target actuators directly? Is it because at some point the signal has to connect to the programming and the electrical, like the one thing is electrical pulses and the other thing is a line in Juliet code. And I am assuming that at some point you need to go through C for the hardware, like very close hardware connection. Is that correct, or how does this interact?
Yeah, that's true. So we have a native function interface where you can write your low-level C code and then call it from within Juliet. One of the benefits of having a more high-level language like Julia or any high-level language really is that you can write libraries and abstract your functions, have people develop these functions separately and provide them to you. And this is something that's, I think, a big benefit of our language is that we have the ability to define new kinds of commands for your gripper, for example, to open close. These can be developed by the developers who use this gripper or the company that produces the tool. With more traditional robot languages, there's a lot of work needed to integrate a new tool into the system so that you can use it at your factory. And I think it will be much simpler with Juliet for independent developers to add new functionalities with libraries.
Well, it sounds like if you have things at a high level, right, and you just say, okay, you're basically just saying how to trajectory plan, how to graph something, how to trajectory plan, put it back here, right? It sounds like a lot of those high level primitives could even be reused for a different robot or a different model. How reproducible or how flexible is this to be able to say, hey, now I swap out the hardware, but I'm still running the same program, right? Because that's always been one of the very big issues with a lot of really low level programming, right? Because it could be so detailed in the actuator, say like, okay, I might want to do the same thing. I'm now just using a different model, but like the way that it runs its controls and stuff, I need to tweak every parameter to be completely different, right? But if you write it at a high level, maybe it works. Is this something that is part of what Juliet is kind of targeting?
Yeah, so it's possible. Sorry, did you want to take this, Philip?
Yeah, I can take this. So multiple dispatch is a cool thing, right? It's in a similar way to how you can define specific types of execution for like static arrays to make things more efficient. We can also define different packages and different interfaces which connect to different types of robo systems. And so we can have what we're developing is one larger like baseline interface. On top of that, you can build specific interfaces with different robot types. So in the end, the user code will look exactly the same, and you just load a different backend depending on which system you're actually interacting with. Is sort of the short answer. So it works well in large part thanks to multiple dispatch.
Well, that's a very new new application, multiple dispatch I hadn't thought of before. So that's definitely a new one here.
I mean, there's Julia for GPU, right? There's Julia for XLA, and now there's Julia for robot. I mean, it's really just moving the same bits around. Having not worked with robot, that seems what needs to be done, right? Moving stuff around. The other question that comes up in this context is, Juliet is partnered with Romeo, which is this virtual machine target. I think you already hinted about at what sort of mechanisms Romeo needs to fulfill in order to make this the real time applicable. When I think of robots, I always think, okay, this is getting closer to the hardware on a whole different level that I'm used to in my daily work. And so I'm always also thinking about, maybe they tinker with Raspberries and Arduinos and all sorts of tinkering hardware, right? So is this also something that comes up in this context? Maybe that okay, right now I have Romeo, but maybe I will deploy it to our Arduino as well.
We're building the language for different hardware targets. So we have a Raspberry Pi build machines that we run it on. And that's important because many of these robot manufacturers use quite underpowered hardware in their teach pendants, the thing you control the robot with, and in the robot controller. You want to save on the hardware costs. So it's important for us to be able to run quickly and performantly with underpowered hardware. And one thing I would like to, if we have time, I would like to develop a x86 backend or ARM backend, so we can build directly a Juliet program directly to run natively on, say, a Raspberry Pi or other embedded systems.
So Romeo is able to run on x86 right now, I guess, but you want to skip the Romeo part of it.
Yeah, that's an idea. If we could strip out Romeo when we're not running specifically robot programs, we need Romeo for that. But if you want to just run some native program on your embedded hardware, it would be nice to use Juliet for that. And it would be suitable. We think it's a suitable language for that, but currently we need this big runtime system. And so the idea is if we could compile to machine assembly for that target, then we could run more efficiently on embedded systems.
Mm-hmm. I assume that a big part of your runtime here, because you mentioned a little bit earlier, one thing that we kind of glossed over a little bit was a whole real time garbage collector, right? So I assume that that's one of the more sophisticated things within the runtime here. I'm wondering if you could talk about a little bit about how such a what are the requirements of the real time garbage collector? How how does it work? And how what kinds of requirements does this put on the embedded kind of usage, right? Because I think that I would assume that like not all embedded devices could support such a piece. So why is this so you know why how is this what are the requirements that this ends up giving to you for these kinds of robotics applications? Like is there size requirements, latency requirements, or I wonder if you could go a little bit into detail there, because it sounds like that really kind of places then where Romeo and Juliet has a lot of its uses, right?
Yeah. So latency requirement is the primary requirement, but we also want to not use too much memory. The systems we're running on, we have a fixed size of memory we can use, and
we're talking about kilobytes here. We're talking about megabytes.
so megabytes, few hundred megabytes typically, or more. So it's not super limited, but we still have to not use. We can't be too frivolous with the memory allocations. But the primary requirement, latency, the garbage collector was designed by Sven Roberts. He worked on the garbage collectors for his PhD, and I think, as far as I know, it's a continuation of his PhD. This garbage collector that we have, it uses these ideas that he was working on a real-time garbage collector before he came to Cognibotics and made the garbage collector for us. But to be able to achieve real-time performance, we call the garbage collector continually. So while running the robot program, we keep calling the garbage collector and asking it to do a little bit of work. And it's a mark sweep garbage collector, so they can incrementally do the marking and mark which objects are live. I think the sweep phase is kind of quick, so the marking is really what takes time, where you have to traverse the whole reference graph of all live objects, and splitting that up into small chunks makes it real time. If the chunks are small enough, then you have a short enough delay, and then you spread that out over the whole execution. So I'm not super into the garbage collector, but I think that's kind of how it works.
Do you have like guarantees on the latency, like the maximal latency of it, or soft guarantees or hard guarantees? Like how clear can you say, like, I know that I'm going to be able to run my controller at 1,000 hertz, even though I'm allocating in this function, right? Like what is like the guarantees that you can actually give to someone in that kind of context?
We have a target. We have a maximum maximum delay that we can have. And this is not just for the garbage collector, it's for the whole, it's for the event service process, where if there is an event, we have to respond to it within a certain time. And we guarantee that by testing on very many different programs that do different kinds of allocations. And it's very difficult to actually prove that you meet these requirements always. But we ensure that we meet the timing by just having very many benchmarks that we run for every commit that we do, that we see that we don't break this.
Okay, so there's some theoretical background, which is Sven's thesis that kind of says, like, okay, this is the way to be able to do such a real-time garbage collector to give you maybe some theoretical guarantees. But then the real world comes into play, and you say, okay, now we have a large benchmark set that shows that this does work in real time. But this is the latency that we could guarantee, known through the empirical measurements that we've done. Sounds like that's the combination that you take there.
And it is possible to prove the timing requirements, but that would be a huge effort. And there's very few companies that do that kind of critical real-time stuff, where they have to prove down to down to like every function
Nanosecond.
has a specific timing.
So it sounds like that. Yeah, that's one major component of the runtime here. But what are some other major pieces within the runtime? It sounds like there's also the trajectory planner that's in the runtime, right? What are the other pieces that kind of come with the runtime for such a robotics language?
It's very similar to a virtual machine. If you think like Java or C#, they have these runtimes. They're called virtual machines, where you compile the language to a bytecode, and then you execute the bytecode instructions in the VM, the virtual. In Java, it's the Java virtual machine. So it's very similar to that. We have a bytecode language we compile down to, and then the Romeo runtime runs the bytecode instructions. It has a whole scheduler built into that, and the scheduler has some considerations for real-time requirements.
Is it? I assume maybe a serial task schedule instead of like a parallel one that Julia's kind of built with, or
Yeah, exactly. It's single-threaded, so only one task runs at a time, and then we're switching using preemption points. We switch between the tasks and the event handler thread.
Yeah, and I assume that's for latency guarantees, right?
Yeah, and it also prevents a lot of different problems you can have when you run in parallel with memory visibility and concurrency issues.
So one thing that I dream about, let's say, is I want to have Julia really all the way in the stack, from the web development and all the numerical shenanigans, of course, but maybe even an operating system, right? Because then we really can throw out all the other languages. Is there a realistic future where Juliet can be used as a operating system programming language?
Kind of. It's possible, of course, but we would really need to have a x86 backend, and then we can bootstrap the compiler. If that's you're thinking about bootstrapping,
so is
having Juliet or Julia all the way down.
So Romeo is currently not written in Juliet.
No, we currently use C. We implemented the Romeo and the compiler. It's two separate things. We implemented them in C, and our partner, the co-creator of this Juliet Romeo system, Estun, they had a requirement. They did not like Rust. I remember we were looking at Rust, and we liked Rust, but we're using C right now.
So it sounds like, though, that it's because you have a virtual machine that you then use to target each of these systems, and that virtual machine is written in C because then it can be portable to a lot of embedded devices and such. But a lot of portability these days tends to come from a lot of LLVM integrations. It sounds like that you don't necessarily use LLVM anywhere in this compiler stack.
No, we do not use LLVM, and there are some things. LLVM is great. It's super useful for targeting different systems, and also with the runtime optimizations that you get almost for free. It's really powerful for developing new languages, but we don't use any kind of runtime optimization, because that plays into the real-time requirements. If you have something where the program has to pause to compile, which can happen when you have a JIT, just-in-time compilation, then you have to pause the program a little bit to optimize a function. So we don't want any kind of pauses for optimizations. And also, optimizing can be very difficult. I'm glad you brought this up. So because it's important to mention that we specifically avoid certain optimizations. We do a little bit of optimization, but it's very important that, for example, a dead statement is still existing in the program, so that we can step to it, because the user can pause the robot at any point and tell it to go to a line that maybe wasn't even reachable in the program, if there's an if false statement, the code inside that if false statement can still be jumped to by the user. And there are and this happens in industry where there can be a little bit of helper code that the developer adds, the robot programmer adds if false, and then he has some code to print out a debug message or to do some specific task. And he wants to be able to jump to this code when he's running the program to handle some problem that might have occurred during runtime.
Or sounds like a very good place to hide Easter eggs, but yeah.
Yeah, that's the exact same term that I was thinking about.
This was kind of mind-blowing to me when I learned about this, because I come from just regular programming, like on your computer. I hadn't worked with robots at all until after my PhD, and then I started learning about programming robots, and I programmed a cobot. We have lots of very experienced people at Cognibotics that have worked many years in industry, and they tell me all these funny stories about like how you can have 10,000 line programs because somebody has a script that generates a program for you where it takes like a complex shape, like an SVG file, and then generates the program from that. Then you get these huge programs. There's lots of fascinating things that happen in robot programming in industry.
I mean, you mentioned that Juliet still has multiple dispatch, I guess, exactly like Julia or very similar to Julia.
Exactly the same, but very similar.
Yeah, so we do have overloading of functions, but we do not have dynamic dispatch right now. And this is something that we are working to add. But so we will hopefully support full multiple dispatch. I don't consider it exactly. It's not exactly the same right now, because you can have an abstract type where you don't know the subtypes, and then we have a problem because we can't know which function will be called.
Your compiler needs to be able at compile time to know at every instance what function will be called.
Yes, so if you have an overloaded function, say you have some abstract type reader, and then you have a string reader or a TCP socket reader, you can have a file reader, you have different subtypes. And if that type is not known at compile time, which function will be called, then you get a compile error. Unless it's a union type. So we have a union dispatch. We do support that, where you can have a union of file reader, string reader, all your different readers. And if it's a union type, then we dynamically dispatch. But we do not dynamically do multiple dispatch at the current moment. But this is something I'm working on, and hopefully will be, when I get back from parental leave, we'll try to add that.
Just to make sure, if you have, you can dispatch on multiple parameters of the function call if they are known at compile time.
Yeah.
Cool.
Okay, and one of the things with multiple dispatch though is that in general, multiple dispatch in Julia tends to have latency if the types are unknown, but then when the types are known, there's a devirtualization that occurs in LLVM, right? And then the code optimizations. Sounds like though, if you don't necessarily have all those optimizations, do you how do you make sure that you still have hit latency requirements, or do you always require that you can devirtualize all the dispatches? Right. So do you get the question there?
Yeah. So right now we require all the dispatches to be specialized on. Yeah. So we can't have a true virtual dispatch, dynamic dispatch, and so we don't have any latency from that. The only thing where we have latency is if you have a union dispatch, but then we have a fixed set of known types. Regardless, it's not a problem that we have a union dispatch, for example, because when we're doing the union dispatch, we can always preempt the task during the
dispatch. That's in Julia. There's the union splitting feature, right? That it turns it into a bunch of if statements, and that can be guaranteed to have certain behaviors.
Yeah, that's exactly what we do. We make a series of if statements, and then the runtime can always preempt during the if statements. So if they're if it needs to take care of some interrupt.
So one of the other things that happens a lot within, Julia and LLVM in general, right, is speculative execution of if statements. Is this something that is just completely disabled within robot usage, or is this something that's like related to the architectures and the CPUs that are run on? I'm curious if any speculative execution, especially of conditionals, occurs.
Yes, we don't disable speculative execution, but that's part of the CPU. So the CPU runs branch prediction, and since we are running in a virtual machine, what it's actually branch predicting is the branches within the Romeo runtime.
Okay.
So it's kind of it's some levels of abstraction there where we don't really control how the CPU is doing things, and you can always configure your machine to disable that if you want really predictable runtime. There are some things you can do on the hardware level where you disable caches and branch prediction, but then the execution gets extremely slow.
Yes, a lot of these features sound very interesting. Especially a lot of these runtime features that are required for hitting certain latency. I wonder if you thought about, like which of these features could actually be upstream to say Juliet, what kinds of open source, kinds of contributions could be done, given a lot of the new ideas coming from here, right? It sounds like there's a lot of certain things that don't necessarily mesh well with Julia, like the single threaded, serial execution, right? Like in having that specific runtime environment. That's definitely specific to the robotics use case. Maybe something like the real time garbage collector, right? Is that something that could be reused in other applications? And I'm curious what kinds of efforts for the open sourcing and then upstreaming has gone on here as well.
Currently, we are closed source. Everything is proprietary, but we would like to contribute to open source. It's kind of difficult right now because we have this co-founder Estun, which is involved, and so it's another industrial partner where we have to be careful about. They have to approve what can be released, and it's a Chinese company. They are much more careful about publishing things, and that's understandable. It's sometimes when we work with them, it can be difficult because they don't share very much about how they use our system. We provide the system, and it's difficult to see how they use it sometimes. But so that's one challenge which makes it difficult to promise anything. But I would like to see the compiler eventually be open source, and maybe that requires a re-implementation. Right now it's written in C, and there are ideas about writing it in Juliet or Julia. So maybe something like that could be contributed. But I don't think it would be difficult to take what we have and integrate it into Julia because it's so different. We don't use LLVM at all, and the Julia compiler is like an extension of LLVM. It uses LLVM very much. Maybe some things with the syntax we could contribute. Like we have a new variable declaration, but it's kind of just a little bit of syntactic sugar. And in Julia, you can write a local to declare a local variable. We have kind of that, but a little bit more advanced because we want to make sure this is a type declaration. So when you declare something, we have a local reader of type reader, then you can't assign a string to that thing. That's an error. In Julia, that's... I forget exactly the specifics, but I think there's some small differences there where you can assign different types that we...
Well, there's type declaration syntax, but yeah, I think so. There's just a lot of discussion going on right now as to what a strict subset of Julia would be, right? To be able to say like at modules, at strict module definitions, to then suddenly be able to say like under a strict module definition, it should act more static in some sense, right? Maybe the discussion around the how that strict subset of language should look. Maybe there's a lot that can be contributed from your experience there of how that should look and behave.
Yeah, maybe. I mean, I think it's an interesting experience taking this dynamic language and seeing how much can we make static. And if I look at some random Julia code, can I run that in Juliet? And often, no, you have to make some changes, but you can often make things work. There are some things that are right now are not possible because of different things with lack of true dynamic dispatch. We can't, for example, read in a type and then dispatch on what that type was. So if you parse something from a stream and it's a string or a boolean, and then you want to send that to you want to add it to an array, and then you have a problem. Well, now we can't dispatch on this type because we don't know what it is. The compiler misses some runtime type information there.
So I assume that your parse functions have to be like, oh, when I parse, you have to give a type to it. You can't runtime check type tags or whatnot from what comes from the stream.
Yeah, so we have implemented a subset of the Julia library. So we can read in. There are these read functions to read from a file, and then you can give a type. So you want to read a int, or you want to read an int 64 or float 64, or you want to read different types. We have implemented those functions, and those are nice because they are type stable. They return as a known type. But then there are other APIs you see where you have a read function and it returns some object, and you don't know what subtype it is. Then you can we can solve that by having an if statement. If x is a string, or if x is a float 64, for example, then we have to have the chain of if statements, or we have to use a union type.
But in both cases, it requires that the user knows what the possible types are. So we have, it's sort of limited dynamics.
Yeah, so you have to close the universe on the types, yeah.
You mentioned that it's proprietary and currently closed source. The program to get access to it will happen this summer. And then the question is, so if I'm now very curious, what do I need to do to get my hands on this, right?
Well, we have a beta program, kind of, where there's an email address somewhere on our website that you can email and be part of the beta tester program. And we're making efforts to, for example, I think one of the ideas is to have a REPL available on our website somewhere, where any user can just boot it up and try things. And if you have some more actual application that you would like to test the language on, you can be part of the beta program, and at some point gain access to some private feedback through there.
And will there also be information about how different Juliet is from Julia, or how much work is there for a Julia programmer to switch to Juliet? Like how much time would Chris need to make differential equations run on Romeo?
For a regular user, it's not that bad. As a Julia programmer, when you're booting up Juliet, you'll notice a couple of things right off the bat. The first thing is every variable declaration has to var. And that's sort of the big difference you'll see immediately. You'll also see that all functions need to have the argument type specified in the signature. So there are some small syntactic things that you need to do in order to have this type stability thing. And beyond that, implementing more advanced things can be done, because it's basically Julia, but a stripped down version of Julia. And there are still some things that are nice and are missing. So, for example, we don't have integration with the linear algebra stuff right now. So we don't support matrix multiplications, for example. But we do support matrices, and that's something we're getting to at some point.
Well, it sounds like if you're that close to Julia, it sounds like you can kind of pull in just like the generic linear algebra.jo or like the generic LU factor stuff, like, because there's all these generic fallbacks that Julia has that are just pure Julia code that aren't calling BLOS. It sounds like porting a lot of those over would not be the most difficult thing. You just have to restrict the types that you allow in there, and boom, you can at least take that, right?
How crazy would the macros look like if I tried to write a transformer from Julia to Juliet code purely in Julia macros? I would assume it is possible, but how scary would it look like?
I don't think that's scary, but it's difficult to translate sometimes because of the need for variable declarations. So there are many cases where you would have a function and you assign something. You need to find where should the variable declaration be inserted. So that's the difficult part.
Yeah.
Like
I guess
people do that from the typed Julia code, right? After Julia runs its lowering passes to type code, it actually comes up with where these variable definitions are in the SSA, right? So you could probably take that SSA and have that.
Yeah, you could do that, but then you would get something that's less like the original code if you take that waveform and translate it.
So if I was to come up with like a really cool scheme for it, right? There is a way where, especially within Cthulhu, right? Cthulhu goes down to typed IR, and then it figures out everything in typed IR, but then it brings that information back up to the original Julia script, right? To be able to show you what all the types look like in the original script.
Okay.
We could, in theory, do a similar thing where you go down to the typed IR and then use that same mapping up to the Julia code, but then also have like the declaration expression. So I think that if you use the internals of Cthulhu, you could actually make this work. But this is opining on something just fun.
And then the function declarations, like possibly you will get insane union types. But if you just macro this away, this doesn't need to look scary in the source code.
Yeah, and it also doesn't necessarily need to be union types. We do support parametric types. So you can do : T, and where the T is, and you can get away with some things similar to true multiple slash with that.
Yeah. So I think that's a lot on the compiler. Was there anything else, Michael, that you wanted to ask about the compiler and the language itself?
In a sense, I'm still asking about if I'm a university and I have a robot lying around, can I get Juliet and Romeo this summer? And what are the conditions that I might need to be aware of? Like, can I publish a paper if using Juliet and Romeo if I want to do some experiments with a robot, or can I apply for grants or stuff like that? Right. So I'm a PhD student. I have a robot. I am sick of programming it in a crazy language, whatever that might look like. Can I use now?
Probably looks like C.
Probably looks worse than C, actually. I think the end goal is to get there, for sure. But I'm not sure about the time frame for that. And I don't think it'll be that easy, like this summer, but at some point, probably.
Okay.
Yeah, I agree. The summer is not. It might be ready for next summer, but there's a lot of integration effort that needs to be done to run it on a new robot, and that would be. So we can't really provide it to someone who has a new robot that it isn't integrated to already, and that's a big difficulty in making a new robot language. Is for industrial robots, there are all these companies like ABB, all these big companies. They have their own solution. ABB has Rapid, and we want to try to sell our language to these manufacturers so they can integrate the language into their system, and then it will spread more. It's a kind of like a network effect. The more of the robots that support our language, the more it will be used. But that's it's difficult. It's difficult to say like when will you be able to use our language. But we have the beta program, and you can get more information if you email us.
Do you have any teaching hardware that you do this with? I know that there's a lot of Swedish kind of groups that do, teaching hardware specifically for control systems, right? Is there any like teaching hardware that you kind of say like, oh, where we are planning to have Juliet and Romeo kind of do this, which is not necessarily a big industrial device, but it's the kind of thing that if you bought this for teaching your students, then Juliet would be the way to do this. It will work.
There used to be a soccer league thing going on with robotics, right? Where you had these Japanese puppies that tried to play soccer, and then these like semi-standardized humanoids that try to play soccer. Like if you could release Juliet and Romeo on one of those platforms, then you could give this to students, I guess.
One thing we are actually working on is developing a full-fledged university course in Juliet, the motion programming language, which I've been involved in. In fall, there will be a course in Lund University via the platform Coursera, which you can take, and you will learn to program Juliet, and you will have access to some, for example, our VS Code extension and an online tool to write and run Juliet code and things like this. So there are definitely things in the works that's coming very soon.
Okay. And this means, Coursera means I don't physically need to be in Lund in order to participate.
Correct.
You could,
Yeah.
you could do it in Lund with Coursera. I mean,
Yeah.
Lund is a very amazing place. I've been there a few times actually. Well, not just from recruiting Frederick and stuff, but also, I mean, and going to the Cognibotics office, which I've done a few times, I think, at this point, right? But I mean, just Lund is a beautiful place. So, yeah, definitely, if people are interested in controls and robotics, it definitely, and they're listening to this and saying like, oh, I don't know where to do a PhD. I would definitely tell people like, yeah, go to Lund. Like, it's a pretty amazing area for a lot of, not just the robotics that you guys are doing, but I mean, it seems like it's just an area that has a lot of this activity going on. So yeah, if you haven't gone, Michael, you definitely should. It's just, I mean, for you, it's just like right across like the little. It's right across the river, right? The Baltic River.
Yeah. I mean,
You should come visit and see our robots.
Yeah.
We have some cool robots at the office.
all right. I see a Cognibotics plane ticket coming my way in the near future, and I'm excited for it.
Yeah, how come we aren't showing any of the robotics and the robots in the background or whatnot? We definitely should be putting some footage of the robots in here.
Yeah.
We'll send you some pictures.
Oh, we don't want pictures. We want it in action. I want to see it gripping.
I mean, this might be a good time to point out that we're recording this on a Swedish national holiday for various reasons, and Jesper and Philip actually will not get paid for working on a holiday, or they do not plan to ask their boss about it. So
No, this is off. This is a side project for me.
Yeah.
According to the American sentiment, Europeans take a holiday every day. So yeah. So one of the other things I wanted to kind of dig into a little bit is, I mean, so Philip, you mentioned before that there are other things that other Juliet culture that has been built around Cognibotics, I think, stemming from Frederick and a lot of his previous work, right? And so I'm curious if you can kind of go into some of the other, what are some of the other things that you do, with Juliet? It sounds like some building and designing some of the trajectory optimization algorithms might be one of these things, or working with some of the controls analyses and such. I wonder if you can go a little bit more into those aspects as well.
Yeah, sure. So I'm part of what our boss refers to as the algorithm team, where we develop algorithms and implement them to run on the VS Code robots. And the way we kind of work is we prototype our algorithms in one language and then translate it. And it just so happens that my closest colleagues are both Python programmers, and I'm a Juliet programmer. So I do my work in Juliet, they do most of their work in Python. And I'm really the only person at the company doing full-time Juliet development. So almost all of our Juliet code is written by me. But as I said, algorithm development, frequency spectrum analysis, model identification, a lot of things like this, more to do with the end goal of implementing low-level control algorithms. Really. And a lot of it, for me, also is in simulation, testing things in a simulated environment. Doing these large optimizations.
Sorry to interrupt. Maybe it would be useful to give like a high-level view of what your optimizations, what your work is about. It's about improving precision, right?
Oh, yeah. Yeah. So the specific thing I'm working on is sort of originally vibration avoidance. So when you have a big serial robot, a robot arm like this, and you want it to move fast, but also be cheap, what you end up with is a robot that moves really fast, but shakes and vibrates both during the movement and after, due to hardware things, due to flexibilities in the gearbox, things like this.
Yeah,
This is
my understanding. Let me see if this understanding is correct. You want the, let's say I want the robot to go right here, right? And so, if it moves really fast, it's going to overshoot it, right? And it's going to go, okay, now I got to go this way, right? And I'm going to overshoot it. It's going to keep on overshooting, and that's where these vibrations come from, or
that's a different thing, really. That's
okay.
the thing you're talking about is tuning these servo controllers,
Mhm.
which is definitely a thing where you need your servo tuning to be to a point where it's fast enough but it doesn't overshoot.
Mhm.
But you can use Juliet quite a lot with the control systems framework to test and implement things like this. But
Mhm.
I work more so with vibrations caused by hardware.
Okay.
So metals that bend a little when they push with a lot of force against each other, and link flexibilities and stuff like this. And so the way to get around that is, there is no really good way in the industry. Because what most companies do is either improve the mechanics and just make the robot stiffer, or use some sort of low pass or notch filters, which aim to remove the problematic frequencies. So that usually results in trajectories not following the original path anymore. Like it's hard to take sharp corners. Everything just kind of blends together and becomes smooth. So we're developing a cool algorithm which does this much better. But it involves having a very rigorous and physically accurate model of the system in question. And so this large optimization, this global optimization that I talked about before, is model identification for such a system with a lot of flexibilities all over.
So I guess there's also a lot of PDE solving involved to get the bodies, the rigid body dynamics for the entire structures.
Well, semi-rigid, right?
Semi-rigid, yeah.
Yeah.
We can get by without solving a lot of PDE specifically, but we do need to numerically integrate a few ODEs.
Sounds like then you're not treating like the rod as a line, but you say, okay, it has multiple joints in here, and as I have different pressures, then I can, the joints can move and they can bend, and I need to learn all the different bendy behaviors with respect to some. I guess it is almost like a 1D discretization of a PD in some sense, right? If I'm understanding it correctly.
Sort of. We try to avoid introducing a lot of flexibilities in the links themselves. The biggest causes of vibrations are twofold. One is in the gearboxes themselves. So if you have a joint, say my wrist moves primarily like this. And if I want to move really fast like this, then because the gearbox inside is a bit flexible, it will cause really fast movements to vibrate. But you can also have things where the mechanics are constructed in a way that it can't just move like this. It can also vibrate a little bit in the other directions, which we can't control directly. And we call these orthogonal vibrations. And they're caused usually by moving other joints, which cause cross-coupling forces and things like this. And so we need to treat these two problems in different ways.
And for treating them, that you're building very high fidelity models of the system using black box global optimization and differential equation solvers. And then once you find this, then you're tuning specific algorithms on those high fidelity models, if I'm understanding correctly.
Yeah, pretty much.
That sounds like a cool use of Julia. So yeah, I think that together I kind of see that, there's a Julia inspired kind of language and compiler, which is for real-time systems, and also control systems analyses, which are then used to be able to, you still have a bit of a two language problem there, right? Because you have to take the optimized algorithm and then be able to turn this into runtime primitives, right? But there's still a lot of new, interesting, faster stuff. At least way faster than the previous world of having to do the analysis and see and check whether it worked. Right.
So the question is now: is the two language problem bigger between Julia and Juliet, or Julia and your Python colleagues, Philip?
I'm still in the boat where I develop in Julia and then implement it in C, eventually. And that does place some limitations on how I can develop in Julia. Because, for example, when I solve ODEs myself, I need to write my own solver to use one of the implemented ones in Julia, because I need to be able to translate it to C. Hopefully, static compilation in Julia gets to a point where I don't need to do that. Because the code runs roughly the same speed in Julia and Juliet, or in Julia and C, if I write the Julia code well. But it's not at the point where we can compile these algorithms. Juliet is currently not fast enough to where it's viable to implement this in Juliet instead and have it run. It still needs to be in C.
And you don't even talk about the Python colleagues, I noticed.
No, they have the same thing where everything in Python needs to be translated to C. I think it's easier to translate Juliet code to C because both languages are not object-oriented. But maybe that's just personal preference.
Mm-hmm. So it sounds like you could be a good user of the. Have you tried using static compiler .jl and some of these static compilation tools for this kind of stuff?
I have. Okay, yeah. And I've been able to do some pretty interesting things with this. But it's hard writing entire algorithms and having everything be static compilable. And it's also hard to do that while keeping the code neat and easy to maintain.
Yeah.
Dynamic.
Yeah, this is one of the reasons for the discussions around having the strict subset of Julia, right?
Yeah.
So the strict subset could be a statically compilable subset. So it sounds like the Cognibotics could have a lot to do in that conversation, and a lot of the use cases coming there.
Yeah, it's certainly something I'm very interested in because I personally would like to get to a point where I don't need to write C. I can just write the code in Julia, compile it, and have it actually run on the system.
And it looks like there's a lot of convergence in different parts of the community where the focus for the next couple of years seems to be very, very similar, and the discussion will happen, I think. So this is really exciting to see. Talking about the next couple of years, so there will be the beta phase starting this summer. Then you mentioned the course that will be happening in the fall. Is there any else that is on the concrete agenda from a Juliet and Romeo perspective, or from Philip, your perspective with the vibration reduction efforts?
From my perspective, we're currently working on bringing this to other types of robots. So we've been primarily developing for one type of robots, and we're looking at other types of robots now and seeing how far we can push this. Because it's a really cool thing.
But for me, it's implementing dynamic dispatch, and that would make it possible to more easily port many more Julia libraries to Juliet. So that's one big goal that we have. But we have very many other things that need to be improved with the language. There are many like small things that still remain to be implemented, like the full matrix notation from Julia. So we support array literals, but not matrix literals, and that would be nice to implement.
Or the full tensor literal. I don't know if you've seen the multicolon syntax.
Yeah, I've seen that. I looked at it a little bit, but I will have to look at it again to really learn how it works. Because right now, I have like a very surface level idea of how the syntax works. But if I'm to implement it in our compiler, I need to parse the syntax and then correctly compile it. So I need to understand it more. What do you think about the matrix notation in Julia? I heard some people really like it, but some people think it's too complicated.
I think that the matrix literal syntax is decent. My only issue with the matrix literal syntax is that matrix literals are the one place where you actually end up having white space sensitive code, because you know that you're in a different column of a matrix because of a space, right? And it turns out that can have some weird parsing behaviors. Like if you're just writing down numbers, you never notice this, but if you're writing mathematical expressions, right? 1 minus 2 versus 1 space minus 2 is a different matrix, right? Because like one of them is one expression versus the other is putting a 1 here and then a minus 2 in the other column, right? And so it ends up actually being the one place that ends up being white space sensitive in the whole language, which is a fun little fact. But it's a consequence of this parsing for literals looking nice, for being able to put a negative number in there. So that's the one little detail that I've always been like, is an interesting detail. I think I had a blog post about this in 2016 called 7 Julia Gotchas and how to handle them. And one of the gotchas was this literal matrix syntax. So I do have one little gripe there, but I think other than that, I actually use it. I use that syntax all the time. I just usually put parentheses around any function that's big enough.
I think do blocks are also white space sensitive. The parameters, if you list them.
Yeah, the parameters of the do blocks are white space sensitive because if you use the parentheses, you get tuples as the arguments rather than the values. So so that do blocks are the one other place that is white space sensitive. Or at least the argument specification for them. Yeah.
So if there's ever a Julia 2.0, then we'll know Chris will be the one that makes matrix non-white space sensitive.
I don't know how you could actually make a really nice matrix literal syntax. It seems like such a hard problem because you need to have different rows and columns and then multi-dimensional tensors.
You could require commas for every, like so 1 comma, space 0, and then you don't actually require the space, right? It's just like the commas tell you the different columns, right?
But then people would complain about writing many commas, maybe.
Yeah, people complain about something there. So yeah, I think like it's like one of those things where it's just like maybe the white space sensitive form is the optimal one, but it is like a thing to be able to say, but it is white space sensitive, so there is an issue that you have to see here, right? That does come up.
I like Julia's syntax. So there are some small things that are a little bit strange. Like you can write arbitrary expressions in many places where you wouldn't expect. I don't remember exactly now. It was a while since I looked at it, but I think you can write very strange expressions as the supertype of a struct. Like you can parenthesize it and.
Oh, the strangest piece that I think that a lot of people don't realize is when you define an array, right? You have like float 64, and then you put the array syntax there, right? Everyone just kind of goes, yeah, that's syntax, right? Turns out that that's not actually syntax of the language at all. All that's doing is it's actually just calling, so like for example, you have like 2x, right? In Julia, you have the implicit multiplication, right? It turns out that this is actually just using it's just lowers to the implicit multiplication syntax, right? So then float 64 times the empty array constructor gives you an undefined array of float 64, and so that's how that's implemented. And like a lot of people don't ever look it up, but it's just like so it's actually just using the rules of the language is the way that this is implemented. And so number types multiplied by array constructor is actually a thing that is just a dispatch that's defined. And that's actually ends up being useful because static arrays, right, that has like the SA that you put in front, right, they implement that in a package because they just overload the multiplication for SA. And so it's like it's a funny little detail that, there's certain things in the language, like it follows this given set of rules. It has this like Lisp kind of thing to it where it's just like, it just follows a set of rules. So if you just define this dispatch, then you're changing how this syntax works because that's just multiplication, right? So there's a few funny things that are in there that, when you dig into it, you're like, oh, this is really cool. But also like, that could have just been syntax rather than just a dispatch on a weird way. But like, okay, if someone tells me, I can figure that out, right? Like, so float 64, I can figure out when someone tells me like, it's the same as 2x, right? But it's definitely an oddity that shows up deep in the internals.
Could I, in principle, also reverse the order, like empty array times type, and then
Yeah. I mean, that dispatch is defined, and so it'll tell you that the error that you get for that is you'll get a dispatch not defined for that multiplication, right?
Okay, I don't know whether I wanted to live in this world. I was happier before I knew that. I think
that's really funny. I had no idea.
So talking about things in a very distant future with a 2.0 version that might or might not change matrix literals, what would be a future for you guys when Cognibotics made so much money from Juliet and Romeo that they can allow you to work on whatever commercially relevant or just they tell you do something interesting that is somehow related to what we do here, but whatever. What would you be working on?
I'm working on the compiler, and what I would really find interesting project would be partly one thing implementing a machine code backend or assembly backend to target embedded systems and to make like a normal executable, build an executable so you can run your program. Like that would be really fun. And then rewriting the compiler in a little bit higher level language, maybe Juliet, maybe Julia. That would be nice. to give it a big refactor, because large code bases, they tend to become crusty, and then you can improve a lot of things if you kind of rewrite parts of it. So that's what I would like to do.
And for me, it's twofold, I guess. One would be to port more of the things from Julia to Juliet that I find myself missing when I program in Juliet. So things like native matrix applications, which currently don't exist, and things like this, and contributing to like writing really useful packages which exist in Julia into Juliet, things like this. And the other thing would be to work on compiling Julia, both static compilation of Julia and also compiling to like binaries. So, for example, the package compiler.jl, you can compile the Julia package to a binary that is a really large one, and it comes with a bunch of SO files, thing like this.
Mhm.
And it would be really, we have several use cases where doing this would be useful, because we have some code generation written in Julia, which generates a bunch of Juliet code. It would be nice to have a really easy way to just port this to whoever without having to send a bunch of different files, or send the Julia code itself and require them to install it. So if it gets to a point where we could compile our entire application to a single executable, that would be really, really cool. And so working on getting there would be fun.
Yeah, and if anyone is still watching this podcast, you made it this far, well, first thing to do is like, comment, and subscribe, right? I got to do the standard YouTuber thing. But the other thing to do is, well, now that you're subscribed and you're on our channel, go back to the previous episode with Jeff Bezenson, where he actually talks about creating small binaries from Julia as a new feature that's going to be released with the next version of Julia, right? So Julia version 1.12 will have a feature for stripping binaries, for being able to make sure you have lean runtime free binaries. The runtime free aspect, I think, is actually 1.13, but much smaller binaries for things like, Hello World and such, being in kilobytes rather than megabytes. So go check out that episode with Jeff, and maybe by the time this episode is released, actually 1.12 might be out there, right? It's in the release candidate for stage. So in about a month or so, like this feature should be actually out there. So maybe we'll have to follow up and see whether it hits your use case or not.
I've been looking at the 1.12 release candidate, trying it to the Julia C compilation, if that's what you were.
Mm-hmm. Yeah, the Julia C compilation with the trimming mode. Yep.
It didn't work too well with the examples I tried. It worked with some very small programs, but it seems like it didn't support some of my example programs.
One of the main issues it has with the release version, if I understand correctly, is that the logging system can be pretty heavy still, right? So if you bring in logging, that will not trim as much. I don't know. I don't think that I ended up getting into version 1.12, and so something like doing certain logging aspects can then bring in a lot of the runtime. Just because then it's like, oh, I need to allocate a few things. So I'm going to bring the JC and I'm going to bring this threading stuff. And so logging is one major aspect there, right? So it really is like, if you have codes without logging, you get pretty lean binaries. If you have codes with logging in it, then you need some way to be able to statically disable that or remove the logging before you do the compilation. But it's close, right? And one of the things that's being discussed is, could we have a separate logging system that's leaner and yada yada yada, and all that kind of stuff.
But to wrap this up, there is still things that Philip can contribute to and have fun time developing. Jesper, there's stuff that you can. There's lots of things to do for you in the future, and in the very immediate future, I think we need to let our guests get back to the Swedish holiday. So if there's no more questions from any of us, I would call this a day. I thank you a lot for your time, in particular for donating your public holiday time. It was great fun. I learned a lot, and I'm really looking forward to see Juliet in action.
For sure. Thanks for having us. It's been super fun.
Yeah, thank you so much. And I also want to say me and Philip are not the only people on the team. We're a large team. Well, not super large, but there are many other people contributing a lot to this work. So they all deserve a lot of credit. And we have, for example, Maya Arvehammar, who's working on the Romeo runtime. She wrote most of that stuff on the compiler. We have also Erik Agneval, who has been helping out with the compiler development, and several others. So thank you to everyone at Cognibotics who helped us get to this point. We wouldn't have such a good language without you.
Yeah, see you next time. Thanks for listening.
Thank you.
Bye.
Bye-bye.
Outro music. Do 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 do.